Please be seated. We are going to start now. Yes, Ahmed has an announcement. Is Ahmed here? No? Okay, can somebody just walk over there and call him?
Okay. So before beginning this session, I thought I would take this opportunity to thank the many people that made this conference a success. I'd like to start with the scientific organizers. That includes Mariana, Leonardo, Suvrat, Eva, Misha, Syok, Shaheen, Marina, Fernando, and also Koji Hashimoto, who contributed a lot to the selection of speakers. If you may, if those organizers can stand up, and we can get a round of applause. You may sit down now. So that's just one aspect of the conference. For the next batch are the local organizers who were really sort of the unsung heroes of this conference. And by that, I am referring to Simon, Lin, and Shoy Yosef. If you guys can come to the stage. Simon and Shoy. Simon and Shoy were in charge of, they were instrumental in selecting the fellowships and the posters, and also in organizing the logistics regarding that. And I think they did a terrific job, so let's thank them again. Also in the background, I'd like to thank the audiovisual team, the camera and media team, the website team, and the microphone runners, and those that were in charge of a lot of the logistics in the background. And many of them are in that corner, so if you can just a round of applause. And last, but definitely not least, is the program manager and Wonder Woman, without which none of this could have happened. I got asked more than once if I am willing to ever organize strings again. Well, if Sundus is available, then yes. Sundus, come on up. Okay, where's Hiroshi? Now we can start the next session.
Okay, so thank you, everyone. So we'll start the next session. The first speaker is Alejandra Castro, and the title of her talk is the aspect of digital quantum gravity. So please.
Okay, very good. So thank you so much for the invitation. I'm very happy to be here. Now, this instance of strings is very unique for several reasons, but one reason that I want to highlight is that I've never been, or in my lifetime, maybe someone will correct me and raise their hand, no, that's not true, but this is the first string conference where I've seen so many talks about de Sitter, which is very inspiring, very encouraging, and I hope it persists in the future. And it's a message to the younger generations that there's beautiful questions and beautiful problems in de Sitter. Now, de Sitter, unfortunately, is also something that makes me terribly confused, and it flips me out. And I will share some of that confusion with you today, but there will be some concrete results. But the reason why I picked this topic is also because I want to have your input. I would like to hear how you react to my confusing statements. Now, the point of the talk will be to compute Euclidean path integrals in the presence of a positive cosmological constant. And there will be two important aspects to the computations that I'm going to present to you. First of all, I'll be including matter fields in my computation, okay? So it's going to be the gravitational path integral in the presence of matter, and then I'll also present to you computations in 4D with a positive cosmological constant, but that has a very nice and interesting connection to the 2D models that we've seen earlier this week. Now, something that is important to mention is that I am not going to be using holography, okay? Every single computation that I'm going to be doing is an honest to God gravitational path integral, and I want to make the two following points with the computations that I'll show you. One, you can get exact results in de Sitter quantum gravity, which is nice. And second is that it is interesting, it is needed to add matter fields to quantum gravity. It's an important aspect of it, and I want to illustrate to you what are the new things that you can learn if you actually add matter field to the picture. Okay, so I did a terrible mistake, and this is basically a 2-in-1 talk, so I want to show to you two results that I'll probably regret because I'm afraid that I'll run out of time. But in any case, let's get started with the first topic that I wanted to present to you, which is basically in de Sitter quantum gravity. And so basically here I want to illustrate how we can advance methods in Chern-Simons theory to get exact answers about quantum gravity in 3 dimensions. This is based on a series of papers with some young collaborators. I will not go through the details, so please, if you're interested, curious, I'll refer you to the papers for the details. Very good. So the problem in question is the following. So we'll be looking at basically matter, the path integral, the Euclidean path integral of, let's say, a scalar field. For simplicity here in the equations, I'll be showing a lot just a massive scalar field. And we basically want to then not just have a QFT on a curved background, we really want to compute that path integral over all the possible metrics. A disclaimer, I'll be doing this on a fixed topology and in 3D gravity today. Okay, now because I'm in 3D gravity, I have a luxury, and the luxury is that I can cast these computations in the Chern-Simons formulation, okay? So I can use aspects of Chern-Simons. And the punchline of this talk is that I'll introduce you a new object, which is we call the Wilson spool, which is the object that captures the matter fields in this Chern-Simons formulation. Now, you could have asked, why did I pick de Sitter 3 in 3D? Well, there's a few reasons. Here I listed 2. One is because I can make use of exact results in Chern-Simons theory. I'm not saying that the 2 theories are equivalent. I'll simply basically take advantage of what we know about SU2 Chern-Simons theory. And the second is that with that power, I'll be able to show to you how we can get G-Newton corrections to these path integrals without using the aid of holography, which is also quite nice. Okay, so let's get started. So how are we going to do this? There's basically 3 steps into this computation. So we want to know, how do I incorporate matter in the Chern-Simons formulation of 3D gravity? So the first thing to do is to just describe the Chern-Simons, how do you describe 3D gravity in Chern-Simons language, just at the classical level. So you basically have, if you're interested in Euclidean DS3, you have 2 copies of SU2. And the important thing to remember here is that the levels, each of the Chern-Simons copy has a level. The imaginary part basically controls G Newton. It controls the Einstein-Hilbert part of the action. And the real part of that level basically controls the gravitational Chern-Simons term. And there's a standard dictionary between how the connections are related to the metric-like variables. Okay? I'll be working on S3. So here I am illustrating what are the connections on S3. They basically correspond to the Euclidean continuation of the static patch that I highlighted here in blue. And the holonomies of these connections are actually not trivial. They're not 0. This is something that I'll mention later on. The holonomies, for instance, around a cycle that wraps the horizon is plus and minus 1. Okay? Very good. Now, second step. We're going to go through this fast. The second step is basically, okay, so that's the metric part of the theory. How do you incorporate particles and fields into this discussion? So the incorporation of particles is something that has been discussed in the past for many years, and the answer is quite natural and simple. They're basically Wilson lines or Wilson loops, where the thing that you have to remember is that the representation, that you pick here in this trace is basically the information that tells you what is the mass and the spin of that particle, okay? Now, in the case of 3D gravity, there's something that is going to be very interesting here as we tweak the computations, is that the representations that you use in SU2 is what we call like non-standard representations. Their Casimirs can be generically complex or real, so they're not your vanilla unitary representations of SU2. But okay, but what we want to do is basically we want to construct fields. Okay, so I want a gravity coupled to local fields. And an intuitive way how you can think about this problem is that if you know how to describe a single particle state, the field is basically the collective of them. So you can think of a field as basically as this particle winding basically n times around it. Now, that's a great intuition to keep in the back of your mind, but it takes actually a little bit more work to develop the whole formalism for the field. I don't have the time to explain you how that all goes, so I'll basically just tell you the final answer, and please look at the papers for how the construction goes. But this is basically what gives rise to what we call the Wilson spool, okay? So the way that we constructed it is by thinking about the one-loop determinant on a fixed background in terms of group theory language, okay? So there's the first step is basically understanding quasi-normal modes of fields in a group theory language, and then relating those quasi-normal modes to poles of the one-loop determinant, okay? That's the 10-second explanation of how it goes. And the answer here, as you go through that beautiful procedure, the final answer is this integral, where you can see here the traces of path order exponentials of the connections, very similar to the Wilson loops, with appropriate representations here picked to characterize the mass of the scalar field. The thing that looks unfamiliar of this formula is that there's this parameter alpha here floating around that goes inside of the trace, and there's this strange measure, and a contour. Basically, what this alpha is doing is it's in this intuitive reasoning of how you think about fields. Basically, as you deform this contour, so the contour is defined by these two red lines, you hit basically poles at integer values of alpha, and this is what gives you, roughly speaking, this intuition that you're winding n times, and so then the field is the collective of the point particles, okay? Very good. But what's really nice about this formula, what I want you to appreciate about it, is that in a sense, I can take it off shell, okay? So the background doesn't have, like the way the connections enter is very, very, very simple, okay? So it's a formula that tells you like, oh, if you change the values of the connection, the one loop determinant will also always be of this form. And this is why it gives you quite a lot of leverage compared to a metric formulation. So it's not just another way how to compute a one loop determinant. Very good. So now let's go to the third step. So we want to know now how to incorporate this into a gravitational path integral, and we'll do that in the Chern-Simons language. So I really now want to show you results related to computing the expectation value of this Wilson spool. So there's three things that you have to keep in mind as you do this, and these are things that we had to adapt from the standard transiemens literature. I do have a complex level here. The background connections, so remember these holonomies that I pointed that there were plus and minus 1. They're non-trivial, so we also have to incorporate that as we do the exact results. And also, I'm using these non-standard representations of SU2, so you have to make sure that also any technique that you use, it's friendly to the modification of those representations. So we actually did it 2 ways, so to see that our answers were sound. So we used the techniques of abelianization by Blum and Thompson and techniques of supersymmetric localization, although there's no fermions, but you can still get inspired by those techniques. And we checked basically, we computed, again, we redid the computations of the path integral on S3, expectation values of Wilson loops on S3, and of Wilson spools with all of these 3 ingredients incorporated. So what are the results? So basically, one question that you can ask after you did the computation is, what is the mass renormalization of this field? So here, we'll characterize the mass of the particle in terms of this variable mu. This is a natural variable that enters in the representation. If you want, is roughly the conformal dimension of the field. And our computations, as we compute exactly what are the effects of gravity, for this point particle, we get an expression of how the mass gets renormalized. And there's 2 things that I want to highlight about this formula. First, there's no G Newton correction to the mass. The first comes at order G Newton square. And something that is interesting is that we're making a prediction. So I don't have a metric counterpart to tell you. So one of the open questions is basically check that in the metric formulation, the 1 loop correction is trivial, and the first correction comes at 2 loops. Now, you can also reverse this picture and say, OK, let's think of it as like you really integrated out a massive degree of freedom. How does G Newton get renormalized? And then, so here I have basically the bare G Newton and the renormalized one. And again, the correction is basically at 2 loops in this sense. And again, this is something that for us, it was basically, it did take some sweat and tears, but not as much as doing Feynman diagrams. And here there's an explicit answer to what are the renormalized quantities. Okay? Very good. So what have I told you right now? So basically, we have a way how to incorporate matter fields in the transiemens formulation of 3D gravity. You can test it when G Newton goes to 0, that it produces the appropriate 1 loop determinant. But we can also make predictions about the quantum corrections. Some things that we're thinking about in the future, in the short future, is to change basically the topology of the space, so do it on lens spaces, which we're working on, doing explicitly the metric computations, so going up to 2 loops and checking that our predictions are correct. And I should also say, I did not talk about ADS3, but the things that we're doing also work on ADS3 gravity, okay? So that's another can of worms, but there's beautiful results there as well. Okay, so second topic. Let's change gears now. So the thing that I want to tell you, the second computation that you can, that is interesting to do regarding path integrals when you have a positive cosmological constant is to look at near extremal black holes in the sitter 4. So what am I going to do here? Basically, I'll do something very simple. So there will be no fancy transiemens theory, nothing esoteric. I have Einstein-Maxwell theory with a positive cosmological constant. We're going to look at some of the very most simplest black holes that you have in this theory, basically black holes that have mass and charge. They're spherically symmetric. And here in this plot, this shaded region is basically the values of M and Q for which you have a black hole. Basically, you don't have a naked singularity, okay? So we're interested in the extremal limits of these black holes. And there's basically 3 types of extremal limits that are the edge of this shark fin. So you can have cold black holes where the inner and the outer horizon coincide, and the near horizon geometry is ADS2 times S2. You can have the Narai limit, which is cosmological horizon equal to outer horizon, which is this line, this dotted line here. And then you also have what's called an ultra-cold limit, which is the little dot at the very, very, very top, okay? So this is kind of fun as a theory because here's where I can connect with the 2D models that have been discussed before. So I can connect with, for instance, ADS2 2D models, DS2, and also Minkowski 2 models, okay? What I'll tell you about today, I'll actually only tell you about these first two branches. Please ask me afterwards why I did not talk about the ultra-cold limit. There's reasons. I'm confused, but any case, yeah, later. So let's talk about these two cases. And so what we're going to do, I'm interested in computing the gravitational path integral in these two cases, and I'm actually going to look at how the gravitational path integral behaves in this near extremal limit, okay? So this is based on beautiful work by Ileshri, Murthy, and Turiachi, and I refer to you also to previous string talks by Luca and Ashok back in 2022 and 2023. Here I'll give a very, very quick overview of what's going on. So we're interested again in the Euclidean path integral. And the observation is that if you do it around the extremal saddle point, so you will, if you do that, you will get a tree-level contribution coming from the extremal solution. And then the first correction is basically it's one loop determinant of the fluctuations of the metric and the gauge field, okay? Now, the observation is that when you do this around the near horizon of extremal black holes, there's infinitely many normalizable zero modes to this one loop determinants. And so technically speaking, if you do this around an extremal black hole, the answer is infinite. And what these authors basically suggest is a way how to regulate, how to tame that infinity. And the way they do it is by basically doing a temperature deformation of the solution. So that's what makes it near extremal. So you deform the background up to linear order in temperature. This will modify basically your fluctuations. And the nice observation is that then the eigenvalues, these are no longer zero modes. So the corrected modes basically get an eigenvalue that is linear in t. And then you can, again, do the Gaussian integral. And you will get basically, for the path integral, a polynomial dependence in t, which is the leading quantum effect. Okay? So this is the philosophy. And let's just do it for black holes in de Sitter. What do you get? Okay, so here's a table with what I'm going to get. So I won't write down the explicit answers because this is where I'm going to illustrate my confusion. But what you should keep in mind here, so we'll go through various different extremal limits. And there's various different types of zero modes that you get. What I'm calling here tensor modes, it's basically what you would get if you're doing the JT sector of DS2, or ADS2, sorry, I should have said. But just whatever I get here, you should compare and correlate with what happened during the talks by Christian and Sandeep, okay? So that's the 2D part of the model. But you also have vector modes, and you also have modes from the gauge field as well, okay? So the higher dimensional perspective basically adds these new other possibilities. Okay, so let's just do the ADS2 case first. And here, basically, what I'm going to be highlighting is if the corrected norm of the zero modes and their eigenvalues, what sign it is, okay? Because what I really want to be able to do, I like to do Gaussian integrals with the right signs up there on the top. And so if you do it around the ADS2 times S2 extremal, this cold limit, basically everything works fine, and you get a correction. No big news, just an academic exercise that I'm capable of doing. Oh, yeah, okay. Now let's go back down here to the Schwarzschild case. So let me turn off the charge, and let's just see what you get in that simplest case if you start doing these one loop corrections. So in this case, what happens here, there's no U1 modes because the black hole is not charged. But what you see here is that these tensor modes have positive norm, but the correction to the eigenvalue is negative. And then these vector modes, in contrast to the ADS2 case, they have negative norm, and the correction to their eigenvalues is also negative, okay? And that's what happens. Now, turn on the charge. Now, when you turn on the charge, there's actually, so what I'm illustrating in these two rows here is that there's different Euclidean saddles that you can look at. How you Wick rotate this de Sitter black hole to Euclidean signature, there's basically two possibilities. And with this like minus and plus signs, and I'm illustrating basically what is the signature overall of each portion is Euclidean, but you get like minus signs in the overall parts. And so depending on how you do the wick rotation, if you pick t or the radial coordinate or both to wick rotate, what happens to the modes is basically a bit different. So this first case parallels a lot what happens in the Schwarzschild case. The vector modes have negative norm. Every eigenvalue is going negative. But for instance, if you do this weird thing where you basically have an overall minus sign in front of the entire Euclidean geometry, at least you get, in this case, the right signs for this part, but then the U1 modes, again, they're a little bit funky. So this is where I will be very happy to talk to people over coffee and tell me, Alejandra, this is what you have to do with this, because I don't know how to do Gaussians when you get the wrong sign. Any case, okay, we can stick factors of i's in various places, but I think the complex properties of this path integral is something that has to be subtle, and I'm not brave enough to fill, I will not fill in what's in here. I will be very happy to hear what you have to say about what should I write down after having done these computations and encountering this problem with these modes. So basically the overview, how am I doing on time? 4, perfect. So basically what I want to convey here is that these black holes are excellent basically at testing and exploring different aspects of how you connect results in 2D models, especially related to cosmology or flat space, to higher dimensional systems. But I should say that I am quite confused about how to think about these quantum corrections and how this actually provides an avenue and a venue to understand really if I'm computing entropy or not. I just decided to compute a gravitational path integral, so I'm not going to tell you that I have a microscopic interpretation, but when you decide to set up this path integral on these extremal backgrounds, their near extremal counterparts do have things that are pathological, and I think they're important to highlight. And you tend to not see them if you're just in 2D. These are effects that you're seeing because you went up to 4 dimensions and accounted for all the relevant modes that are around. So with that, let me conclude. So the way that I wanted to conclude is basically by giving you some future directions on each of the 2 topics that I talked about. So the first topic that I touched upon was the case of the Sitter quantum gravity coupled to matter, and I think there's quite a lot of interesting things to explore there. The first one is basically, well, there's many, but one of them that I should highlight because I always get asked this question. What I did with this Wilson spool is compute the expectation value of the log of the partition function of, for instance, the scalar of this matter field. But ideally, what we want to do is really compute the expectation value of that path integral itself, so one has to be careful. I do think that there's something nice to do here in terms of its microscopic interpretation, given that we have exact results and we can do these computations quite carefully. It will be nice to understand what are these as 3 partition functions compute. I encourage you also to talk to Dio about this because he has a really nice vision on this topic. And also, in the case of ADS3, we can do the computations classically and semi-classically, but it will be also really interesting to incorporate the quantum corrections in the case of ADS3. So there it's a little bit more subtle. I don't have that many, well, I don't have exact results in SL2 Chern-Simons theory, or if one wants to use a different TQFT, so that's a different can of worms. But okay. Then in regards to these the Sitter 4 black holes, I do think the results that we're getting deserve some type of microscopic interpretation and how to understand if you're telling me, no, just do appropriate analytic continuations. In some cases we can, but it's still, I'm not fully convinced, but any case. I think the fact that we're getting some pathologies in these quantum corrections deserves an explanation. And also, I do think a nice case to study that deserves attention is this ultra-cold limit as a playground to understanding basically properties of quantum gravity and flat space. So it's a really nice toy model for that point of view. So with that, I'm done. Thank you.
Thank you very much. So we have time for discussion. Yes, Sandeep?
Thanks a lot, Alejandra. So I had a question about the second part of your talk. If you take, say, this near Narai limit, you had for the gauge field a negative norm. And I didn't understand that because you're starting in 4D with the usual sign for the kinetic energy term. You're doing a dimensional reduction. So why did you get a negative norm?
It's just because of like how the signs come in the action. Like, yeah. So if amenity is 2 times S2, everything was just fine. Like the norm of that U1 had the right sign. It was positive. So in the first.
Yeah, in the first, but towards the end of the table.
Yeah, but then it went it went bananas.
So if you took the uncharged case,
the uncharged case doesn't have a U1 mode to talk about. So I don't have anything. So this last column here, I don't have anything to say about the U1 mode.
Oh, I see. So the vector modes were coming from the.
Yeah, so they're coming like from like the charge Rice Nostrum. Yeah.
Okay.
Any other question? Okay.
Yeah. Well, okay.
Oh, okay. Oh.
Back here. Hi, Hiroshi.
Oh, you are signed. Yeah. Okay. So Daniel, you can speak if you want.
Yeah. Hi, Alejandra.
Where are you?
Back here.
Sorry. Okay.
Also about the second part. So my understanding was that the Euclidean de Sitter-Schwarzschild is singular because the horizon of the de Sitter and the horizon of the black hole are at different temperatures. So there's a conical defect.
So I'm going to the extremal limit. So I
thought you're near extremal. So.
Well, then I can just kind of move a little bit away. So I'm moving away if you wanted the Milne patch.
But it's not a little bit singular if you do that?
But yeah, so it depends. You can also ask this question in the normal black holes, right? But the way that we move away from extremality, like in the normal black hole, you have our plus and our minus, right? And so the way that we move away from extremality is by basically being outside of the outer horizon, and then you don't see the inner horizon.
No, but I'm not concerned about that. It's the cosmological horizon.
Yeah, but okay, so I'm not going back into the static patch. Let me put it that way.
Oh, I see. You're not going up.
Yeah, so I'm going up to the, like when I move away from extremality, I'm basically going upwards to I'm in the Milne patch basically when I'm doing the computation, if that helps you.
Okay, so you exclude the exterior of the black hole from the calculation.
Yeah.
Okay, next question.
Hi, Alejandra. I'm also a question about the second part.
Nobody cares about 3D gravity.
Well, it's the first part great. I think it seems very natural that you have the minus sign because Narai black holes at the extremality is not thermodynamically stable. Like.
Oh, you think that this is coming, that this minus sign is an thermodynamic instability of the...
Yeah, because black hole can be hotter and the horizon
It could be. The thing that, for instance, in these two cases, it depended on how I basically decided to analytically continue it. So this is basically, it's the same. So these two cases are the same solution, but I just decided to Wick rotate them in a different way. So I don't know if maybe you would say, I did a Wick rotation now such that it's thermodynamically stable now. But yeah, that might be a good, I'll be happy to chat more about you about that.
Okay, thanks a lot for the great talk. So I know I'm a total broken record on this, but with any kind of apparent pathology of de Sitter space, lately people have been finding that putting a time-like feature helps with it, so a time-like boundary or maybe even just an observer. So I'm sorry I'm slow on the details, particularly the second part.
I went very fast, so don't know.
No, I mean, would that potentially be something that would help make more sense?
It could be. It could be that I'm not computing. So this is always a problem in de Sitter as well. Like maybe this was not the right computation. In the sense of like I didn't put the right boundary condition. I didn't set up correctly the path
exactly. The doing what I'm asking changes the boundary conditions and therefore can in principle change these kinds of...
And maybe I don't... It might be worth thinking about it because these zero modes are very sensitive to boundary conditions. So
I'll take one more question from Shiraz.
Okay, what's probably a very stupid question about the first part.
Thank you.
You were talking about working in sort of funny representations.
Yes.
So now, if you had a scalar field, I would have naively expected the representation to be one-dimensional because that's just one mode of the scalar field. Yeah. I suppose that's wrong. Why not?
Well, one-dimensional, so you have, it's one-dimensional with respect to each copy of SU2, if you want. But So you have like a ladder operator on each copy of SU2. So they look like highest weight representations for each of them. But
so in the second quantized formulation, there would be a field with a label, with many labels, and that would describe a scalar field?
a field with many like the
Representation labels. Sorry.
well, the representation. So for a scalar field, you just have like there's just so for the two copies of transaminds, in principle, you have two different Casimirs, and so I'm picking the Casimirs to be the same, and that's the mass of the field, if you want. But I think you're asking me something. Oh, okay. Sorry that the one question on 3D.
Okay,
failed.
thank you very much. Okay, so let's thank the speaker again. So the next speaker is Yu Nakayama, and the long title, Scale versus Conformal in Nonlinear Sigma Model, Dipole Magnet, and Parisi-Sourlas Supertranslation. Please.
Thank you very much. And first of all, I'd like to thank the organizers for this wonderful string conference in Abu Dhabi. It's my greatest pleasure to be here. And one apology is I changed the title of my talk. Oops. And this is because on Wednesday, I found that many of us use the terminology supertranslation for asymptotic symmetry, not for the scalar supersymmetry I'm talking about. So I acknowledge your priority, and I changed the title of my talk. So with this, let me begin. And I believe most of you learned string theory by reading Polchinski's book. And I'd like to check whether you have solved the exercises. And I found exercise 15.12 very interesting. It reads, for massless graviton vertex operator, find a weaker condition for invariance under rigid Ward transformations and find solutions. And here, what Polchinski meant by rigid Ward transformation is what I would call scale invariance without conformal invariance. And you should be able to solve it, but since this particular problem is not solved in famous Matt Heydrich's solution manual, which you can find here, let me show you the quick answer. And so I'm focusing on a traceless graviton vertex operator in bosonic string theory like this. And if you demand scale invariance, this operator must have dimension 2, which means that k squared is 0, or k is a null vector or light-like vector. Good. If you require conformal invariance, you have one additional constraint, which is this polarization tensor must be transverse. If you know anything about the string theory, you realize that having this transversality constraint is crucial in getting rid of negative normal states in string theory. So what Polchinski wanted you to learn here is that first, there is a clear distinction between scale invariance and conformal invariance. And second, the distinction is important. But here is one interesting observation. Suppose we were working in a Euclidean signature, compact target space. Then k squared equals 0 means k itself vanishes. And there is no constraint from the transversality because anything is transverse to 0. In other words, scale invariance does imply conformal invariance in this particular situation. This is in accordance with the general theorem that pursued by these authors, in particular by Polchinski, that scale invariance does imply conformal invariance in generic QFTs in 2 dimensions with some assumptions. Things will be a little bit more interesting if you study the curved space-time. And as you know, if you consider the 2-dimensional nonlinear sigma model, the condition for conformal invariance is that the target space has a Ricci flat metric like this. If you only require scale invariance, you will get a weaker condition. The Ricci tensor doesn't have to vanish. It can be given by a Lie derivative of the metric under a certain vector field V. And so such a manifold is sometimes called quasi-Ricci flat. This term is from Friedan. And nowadays, mathematicians would call it steady Ricci soliton. When this vector field V is gradient, then one can introduce the Dilaton coupling to improve the energy momentum tensor and make it conformal invariant. And such a manifold is called Ricci soliton of a gradient type. And here is an interesting classical mathematical theorem in differential geometry. It says compact Ricci solitons are all of gradient types, meaning scale invariance implies conformal invariance. And this classical theorem was revisited by Perelman later by using the C function for the 2D nonlinear sigma model. And this approach is closer to what Polchinski did in the generic QFTs in 2 dimensions. And there are also more recent discussions by these authors, Papadopoulos and Witten, and to pursue this idea further, including B field, higher derivative corrections, and supersymmetry. But in my opinion, things will be more interesting, more non-trivial, if you consider the situations in 2 plus epsilon dimensions and 3 dimensions in mind, eventually. Here, if you have a nonlinear sigma model in 2 plus epsilon dimensions, the condition for scale invariance becomes like this. The only difference is we have added this classical term. When epsilon is negative, closer to 1 dimension, things are as easy as in 2 dimension or 0 epsilon case. And you can use the same trick in differential geometry, and then by doing simple analysis, you can show that there is no expanding non-gradient Ricci soliton, meaning that all the solutions of this equation with negative epsilon has trivial vector field V, so scale implies conformal invariance here. But if you study the situation with positive epsilon, things will become much more difficult and significantly more difficult. And the corresponding mathematical problem was first solved around 2002 by Perelman in his seminal work on the Poincare conjecture. And there was a related session on the Perelman's work and Poincare conjecture in string conference in 2006 in Beijing. For me, what Perelman showed is that if you consider a compact shrinking Ricci soliton or the manifold that solves this equation are of all gradient type. Again, physically meaning scale invariance does imply conformal invariance in 2 plus epsilon dimensions in this particular class of theories. This result is significant because in 2 dimensions we know the Polchinski theorem, but in 2 plus epsilon dimensions, physicists do not know whether scale invariance should or should not imply conformal invariance. So this result is for physicists, it is a great theorem by mathematician. And in his study, Perelman introduced the concept of entropy, W entropy, defined like this, and studied this monotonicity and concluded this theorem. At that time, we were not sure what this Perelman's entropy mean. And in my understanding today, this Perelman's entropy is not the C function in 2 plus epsilon dimensions, but it is rather try to distinguish scale invariance and conformal invariance directly in these 2 plus epsilon dimensions. And if you have a conformal fixed point corresponding to these solutions, then you can show that Perelman showed that this entropy is stationary. And if you have a hypothetical scale invariant but not conformal invariant solutions, then this is not stationary and so on. Today, I'd like to discuss the further general structures of scale invariance and conformal invariance. Excuse me. And so in particular, I'd like to understand what is the signature of having scale invariance without conformal invariance in general QFTs, and I'd like to confront one puzzle here. So suppose it is a good idea to talk about the response to the wire transformation of your QFT to discuss the distinction between scalar invariance and conformal invariance. In particular, if suppose the response to the wire transformation is given by a total derivative like this, this is the most interesting situation we'd like to focus on. And in the case of the scalar invariant nonlinear sigma model, this vector operator V is nothing but the pullback of the vector field that appeared on the right-hand side of the scalar invariant fixed point equations. If you look at this response, you first realize that it is a symmetry if this delta sigma of the wire factor is a constant, because you can do the integration by part. But if this delta sigma were non-trivial function, such as the case for the special conformal transformation, you cannot do the integration by parts, so it is not a symmetry. In terms of the operator language, this tells you that if the trace of the energy momentum tensor is given by a divergence of a certain vector operator, you have scalar invariance without conformal invariance. And this vector operator V is, for historical reasons, called virial current, although it is not conserved. And here is a puzzle. If you look at this equation, you first realize that the dimension of the energy momentum tensor must be D exactly. And then this equation tells you that the dimension of the vector operator V must be D minus 1 exactly. Suppose you are able to find an example of scalar invariance without conformal invariance in interacting theories, then you got a puzzle, because what we learned in QFT textbook and what you teach in QFT course is that if you have interactions, all the operators will get anomalous dimensions. And the only exception is that such operator is conserved. But here, we are talking about the non-conserved operators. And is there any reason to have a non-conserved operator which has 0 anomalous dimensions? Can we have such a theory? Indeed, this becomes a certain obstructions to have scalar invariant but not conformal field theory with interactions. And is there any clever mechanism to protect the dimensions of non-conserved vector operators? That sounds technically interesting to me if you are interested in the general structures of QFT. And in the rest of my talk, I'm going to show you 2 examples of scalar invariance without conformal invariance in interacting field theory to see whether there is any mechanism to do this. Before doing it, I have one slide for you. Over the last decade or so, there have been significant progress to understand the relation between scalar invariance and conformal invariance, in particular in 4 dimensions, and with some assumptions. And there are many people who contributed it. And the basic idea is closely related to the proof of A theorem by Komorogotski and Schwimmer. And the very rough idea is that if you have a scalar invariance without conformal invariance in 4D, A decreases forever, which sounds absurd. And this is okay, but my focus today is 3-dimension, first of all. And I'm statistical models without reflection positivity or unitarity in mind. So although I'm going to show you some examples of scale without conformal invariance in the rest of my talk, they do not contradict the discussions there. But I'd like to also emphasize that my examples are realized actually in real material or in nature. So they may be very interesting things to be pursued. So the first example is realized in the so-called dipolar magnet. And this dipolar magnet is done in collaboration with Aleix Jimenez-Grau and Slava Rychkov. So we are talking about the refinement of the Heisenberg magnet, or 3 models. And this was first suggested by Aharoni and Fisher. And they argued that there is one missing effect in our understanding of the magnet realized by Heisenberg theory. And the one effect missing was the photon exchange. So Heisenberg model only discusses the short-range interaction, but in reality, there is an electromagnetic field that is exchanged between spins. And this will give you a long-range interaction, although it is very weak, but it is relevant in the resistance. So if you are working, if you would like to really understand the phase structure of the phase transition, you cannot neglect it. This is what they said. And they further argued that this effect will eventually make the spin vector or magnetization vector transverse in the far infrared limit. All in all, what it tells you is that in order to study the critical behavior of the magnet, you have to study the Landau-Ginzburg theory or some effective theory with magnetization vector or spin vector, but with extra constraints that gives you the transversality. Now, if you add this constraint, the structure of the fixed point will change. And what we found in our paper is that this fixed point, so-called dipolar fixed point, is scale invariant, but not conformal invariant. And the basic reason why this is not conformal invariant is that this transversality constraint is not consistent with conformal transformation. Alternatively, you can study correlation functions, 2-point function, 3-point functions, and to conclude that they are of not conformal form. I want to mention here that there exists real material, such as europium compounds, that showed these transverse constraints in the spin polarization, and then they are examples of scale invariance without conformal invariance in nature. And we may wonder why the more conventional ferromagnet, like iron or nickel, may or may not show this behavior, and we haven't seen it yet in experiments, because the Bayer value of this dipolar effect is too small, but our theory suggests eventually we will be able to see this effect in this more conventional material. But my focus today is why there is any vector operator which is not conserved, but is protected in this interacting field theories. So here is this theory, and if you look at the energy momentum tensor, you realize that the Villiard current is given by a product of this Lagrange multiplier U and this magnetization vector or spin vector phi. So this is the Villiard current. And of course, this is not conserved. And if you study the compute, the anomalous dimension, you get 0. What is happening? Well, this theory has a very special property, a shift symmetry. If you shift this Lagrange multiplier by a constant, you know that this will give you the symmetry of this action. In other words, there is a Noether current corresponding to the shift symmetry given by this magnetization vector or spin vector itself. And now you can study the Ward identities, Ward-Takahashi identities for this shift symmetry. So you have shift charge here, and you have Villiard current here, and this gives a shift of the Villiard current, which is given by the magnetization vector itself. And if you compare the dimensions of left-hand side and right-hand side, you realize that in this particular situation, the dimension of the Villiard current is exactly d-1. This is interesting because usually you say that if you have a conserved current, this conserved current is protected. But something different is happening. If you have a conserved current, this conserved current protects some other operators. So this is one interesting way to realize this non-renormalization of the non-conserved operator in QFTs. And this mechanism appears everywhere. And my conjecture is that if you have interacting fixed points with shift symmetries like this, they are most likely scale invariant, but not conformal invariant. And you can find some examples in higher derivative fixed points with some higher derivative interactions. Okay, so Another example I'd like to discuss is the Parisi-Sourlas supersymmetry and realized in random systems. And Parisi and Sourlas are interested in some statistical average of certain stochastic PDE. So, for example, you can take any field theory equations like this, and then they are sourced by random force on the right-hand side like this. And then introduce some random measure for H and study the ensemble average. And you can make this question into a field theory, quantum field theory, by first introduce the Lagrange multiplier omega to make this constraint into the form of the action by exponentiating it. And then further, there is a Jacobian factor for the constraint, but you can also uplift this Jacobian into the pheromonic path integral by using the standard Fadeev-Popov-like trick. And further, what they noticed is that a resulting action has a scalar supersymmetry. This is what is called the Parisi-Sourlas supersymmetry, or Parisi-Sourlas supertranslation symmetry. And what we'd like to do is to find the critical behavior of these stochastic theories. And to do this, again, you can do the path integral, and then I'm going to do it in the epsilon expansions near 4 dimensions, introducing 4 coupling constants that are necessary for the renormalizability, and fine-tuning the parameters and random source, and we can find these beta functions for 4 coupling constants at one loop order. Now, if we demand beta functions to vanish at one loop order, I obtain one fixed point located at here, and which is a conformal fixed point. So not very interesting. But it turns out this is not the only way to find scale invariant fixed point in generic QFTs. So demanding beta functions to vanish, all vanish, is too strong to look for scale invariant fixed points. The reason is the response to the scale transformation can be a total derivative. So if the beta functions can be rewritten into the total derivative form, it still gives you a fixed point. And in this theory, there is one free parameter you can introduce here with this trick. And I'd like to emphasize that this idea is more generic, and if you have any beta functions in the next time, you may want to try this analysis, and you may find more fixed points. But anyway, I tried this in this model, and we have extra parameter can be introduced on the right-hand side in the fixed point equations. And what I found is that there are 8 additional scale invariant, but not conformal fixed points in this particular theory. And these theories have a very interesting properties. These fixed points have very interesting properties, which have the analog of renormalization group cycles studied by these authors. But in this talk, I'd like to focus on the non-renormalization of the Villiers current operator. So let me focus on this. So in this theory, we have the Villiers current realized by this the vector operator constructed out of these bosonic fields. And this is not conserved. And why does it have 0 anomalous dimensions? And the reason is that if you study the supersymmetric transformation of these non-conserved operators, you will get a conserved supercurrent. And if you can write down the Ward-Takahashi identity for this supersymmetry transformation. So you have this super charge here, and you have this Villiers current. If you do the supersymmetry transformation of the Villiers current, what you get is a supercurrent. And again, if you compare the dimension of the left-hand side and right-hand side, you can realize that the dimension of this Villiers current operator is exactly d-1. This is, again, interesting new idea to protect the dimension of the non-conserved operator. As in the shift symmetry, this scalar supersymmetry tries to protect the dimension of other operators. And this argument is non-perturbative, so it does not rely on the perturbation theory. Of course, you can check the dimensions of this operator in perturbation theory, and you realize that somehow this operator is not renormalized, although you have interacting field theories at a fixed point. Okay, so let me summarize my talk. It is generally believed that scalar invariance should imply conformal invariance in sufficiently good interacting field theories. But if you relax some of the assumptions, like unitarity, as I did, scalar invariance without conformal invariance may exist in interacting QFTs in particular. But this is puzzling because, as I said many times, it requires an existence of non-conserved operator with protected dimensions. This is very difficult to find in generically interacting field theories. At the same time, if you find such an examples, there should be some interesting way to protect operators. And I found a couple of clever mechanisms to protect the non-conserved operators, such as shift symmetry or scalar supersymmetry. And there may be more interesting examples to be found. And in relation to the string theory and in relation to the supersymmetry that we expect in high dimensions or in string compactifications, I'd like to say that the scalar supersymmetry appears in many examples, such as topological twist. And in particular, I'd like to mention that in the original paper by Witten on the topological twist, he mentioned that if you do the topological twist, conformal symmetry will be lost. And so I would expect there should be many more interesting examples of scalar invariance without conformal invariance with the help of the topological twist. My final word here is that don't be afraid of non-unitarity. And as I showed, there may be many interesting physical realizations of non-unitary or non-reflective positive theories. And also they have many interesting behaviors that we may not expect with unitarity. And in the afternoon, I think there is a related comment by Professor Klebanov. So with this, let me stop here. Thank you.
Thank you very much. Any question? We can take some questions. Okay. Over there. There.
Did you study consequences of scalar invariance without conformal invariance? Like, for example, is there still convergent operator product expansion, what is some analog of conformal blocks or things like this in these theories?
Generally, no. It's more difficult. And we cannot, for example, use the conformal bootstrap to solve all these theories. But OPE, maybe. But the convergence is not so clear.
Okay. Any other question? Can take one or two. Okay. Yeah. Sasha.
Your first example of dipolar magnet.
Yes.
Do you have examples in other number of space-time dimensions? So what happens there? So you presented this 3D example.
Yes. Well, this analysis is based on epsilon expansions, and you may be able to do the similar analysis down to 2 dimensions, but there is a Marmin-Wagner theorem, so there may be no such examples in 2 dimensions. So, and in higher dimensions, well, some of you studied the 5D ON fixed point, and so maybe there is some related fixed points. Or maybe if you allow imaginary coupling, then similar to the phi cube theory in near 6 dimension can have such a behavior.
Okay. Okay. No more question. If not, let's thank the speaker. Okay, the final speaker of this session is Elli Pomoni, and the title of her talk is Exploring Thermal CFTs. Please.
I should start by thanking the organizers. It's a great pleasure to be here, and I have already learned many things. This is work done with these wonderful people, and especially the three younger ones are the thermal heroes. They have done all the calculations, so the credit should go to them. The motivation, I mean, basically is not needed in this audience, but let me go ahead anyway. So we know that quantum critical systems are seen in the lab, and many of them are seen in non-zero temperature, so we really need to learn how to calculate at finite temperature. If we want to learn about black holes using the ADS-CFT in higher dimensions, I mean, in low D there is beautiful success, but in higher D we really need to clean up our act. And also in general is a very beautiful question to ask. Can we place CFTs in non-trivial manifolds? And the manifold on which I want to put my theory in order to capture my thermal effects is S1 times RD minus 1, and this is the next step after just flat. And this is the easiest way to study to turn on the temperature, but immediately once you do it, you see that you break all the nice symmetries that we used in order to use the conformal bootstrap. In this talk, what I want to do is that I will assume that the zero temperature thermal bootstrap is done, so our bootstrap friends can give us a list of all conformal dimensions and three-point functions. And what I want to do is that I want to ask if we can now compute the new due to finite temperature data. And these are thermal one-point functions that are, these forms of the one-point functions are fixed by the leftover symmetry, and this is a neutral scalar, and generically you get something when you have traceless symmetric tensors. Now, what is good for us is that we still have the OPE, and we will use it. There is only one thing that we need to be careful, and remember that now in this time it has a finite radius on convergence. And this picture is taken from basically the paper that started the field. Now, what do? We take, for example, a two-point function of two identical scalars, we OPE, and now we have non-zero vevs in the right-hand side. We plug in the formula that we have from symmetries, and we obtain this very beautiful formula, which is our two-point function conformal block for two identical scalars when the temperature is not zero. So this is one of the main formulas that I will use in this work. And all the non-zero temperature data is captured in this A of O. We know another thing which is very important, and this will be my main friend, and this is the KMS condition, which is the condition that captures the periodicity. And as it was observed already in this very beautiful paper, the OPE expression that I just showed here is not manifestly KMS invariant. So what we should do is we should use KMS as an extra non-trivial condition to get a handle on the A's. And you can think of it as a thermal crossing, an analog of the thermal crossing. And from what I will do in the rest of the work, I will use this version of the KMS condition, which is nice because I can OPE from both sides. So now this is the plan of the talk. I will first derive and also test and learn from this testing some rules, thermal thumb rules. Then I will turn my attention to heavy operators, and I will see that we can compute an asymptotically thermal OPE density. Having learned a beautiful lesson that is coming here, I will propose a new numerical method for the thermal bootstrap, which is very efficient, as we'll see, very quick, and everybody can do it. And then I will say a little bit about Polyakov loops. So let's begin with the sum rules. So we use this version of the KMS, as I already said, and with a tiny little bit of manipulation, we can bring this equation to this form, where this function f is explicitly written here. We know it very well. This equation is this actually is an infinite set of equations for any integer n and odd L. is an infinite set of equations that are linear in the new finite temperature data. And this bit that has all the known zero temperature data is known. Yeah, so it's a very nice set of equations that we can try to solve. It has one difficulty, and this one difficulty, as opposed to the zero temperature bootstrap, is that the thermal one-point functions do not have to be positive definite. Just for the people that are not doing bootstrap in their everyday life, the fact that we have these integers comes from the fact that you can think of these expansions are taking derivative with respect to tau and with respect to r. Perfect. There is another thing that you can do to simplify a little bit these sum rules, and then you can even play on a piece of paper with them, and that is to just ask to study them when you go to the zero spatial coordinates, so you can think that you are on the same circle. And then they take this very beautiful form. There is only one price to pay when you do this game, is that now you don't have A of O, you have A delta, which is the sum of operators. So operators with the same delta, but different spins, cannot be distinguished because I killed R. Generically, this is not a problem, because in order for something like this to happen, you need extra symmetry. And for example, this is what happens in free theories, but it's okay, we know how to solve free theories, so no problem. Now let's plot a little bit. So test our some rules, but also learn a little bit of a new lesson. In fact, there are more lessons, but I will just stress only one. So first we plot the left-hand side, and these are these dashed lines everywhere. And this is the identity contribution. And then on the right-hand side, we have the sum. We will start adding operators and see how we actually satisfy our sum rule. And one of the most important lessons for the rest of the talk is that when L is small, you can see here, for example, 1, 2, 3, 4, this is L equal to 1. Only with a very few light operators, you can actually have approximately satisfied your sum rule. Okay, so this is something we remember for the light operators, and now we turn to the heavy operators, and here we will learn another very nice thing. And this work is inspired by this beautiful paper, and because Sasha is here also, we learned from his paper, and Pal, we also had correspondence, many beautiful papers on the Tauberian theorem. And so what do? We want to find a way to bound the thermal OPE density as delta goes to infinity. So to do that, again, we do our nice trick. We set R to 0, and we route our two-point function in this very beautiful way, and then introduce a spectral density. So in the end, we have this form. Again, remember, I am losing my way to tell people with different spin, but the same delta, but it's okay. Now, this is a tiny little bit that everyone knows, but I will just need it in a second. I need the poles of the two-point function on the real axis, and these are these because of periodicity. This is very simple. And now what do? I will make an ansatz for the asymptotic behavior of the density. Of course, if you had never studied Tauberian or if you have never played with these things in any way, maybe you wouldn't easily make this ansatz, but I have, so I can do this. So make this ansatz, and then just simply do the integral and compare with the poles that I showed you before. This gives you the answer for the spectral density. So this is our beautiful result. We should remember that, of course, we have a discrete spectrum, yeah? So this is just an average density, but that's great. And then I can do this integral, and this is the answer. And this box is actually correct formally mathematical results, which goes under the names Tauberian theorems. And not only you get this, they come with an error, yeah, which is really great, and I'm going to use. Now, what I did is super heuristic, but you can read the paper for a more rigorous treatment, where we use Tauberian theorems to derive what I showed before. And the only thing we need to do is we need to make these assumptions, so unitarity, so reality of the OPE coefficients, boundedness, which means that Even if some of the operators, the A's goes to negative, still they are bounded from below by a negative but finite number. And then this is also a little bit important, and it has to do with unitarity. When d is equal to 3, the free theory saturates this bound, but we know how to solve the free, so we don't care anymore, so this is also perfect. Now, let's, with the theories that we know how to solve, let's see what this is. So let's first of all do a free four-dimensional theory. We know the exact answer. And here I write the Tauberian approximation. And you just look at the plots. Here we have the partial sums as a function of the spin, and here really the plot of the two-point function and the Tauberian approximation. It is an approximation, but it looks already very good. Yeah? The same thing you can do for the ON model. This audience doesn't need introduction to what the ON model means, but maybe you need to know that Satchev and collaborators, and also this paper, they have written down the two-point function, so we also know the exact two-point function there. One tiny little thing that we did that is cute is that at the r equal to 0, we brought it into this very nice closed form. Okay, this is just a cute curiosity. But then we plot, this is the red, the Tauberian approximation. The blue is the exact result. And you see, only a tiny little bit of the first few light operators do something that is not good, and all the other operators go with the Tauberian super well. So, and the same thing you can also do for the full two-point function, plot it, and you see that the error is less than 10%. So Tauberian approximation by itself is very, very good. Inspired by these things, one is the little lessons from the light operators, and the other is the big lesson from the Tauberian. I want to propose now a new way to do numerics, and this is the following. So first of all, I want my machine to have as an input the zero temperature spectrum, which my bootstrap friend will give me. And then as an output, I will have all the 8 deltas and some other parameters that I will explain in a moment what it is. And then what is the name of the game? We will truncate the sum rule into a bit that captures the light operators. So here is in this plot, this bit, and this is what I need to solve for. And then the heavy operators that obey the Tauberian tail, I will know what they are using Tauberian. And in fact, not just Tauberian, I will even improve by adding corrections. Yeah? So C here is this C that I want to have as an output. So, and then this is the starting point. And just numerically minimize with random coefficients and see what you get. Yeah? So let's do it. First, we do our friend theories that we know the exact result for. So this is free theory in 4 dimensions. The result is amazing. Then 2D. 2D is very good because we also know how to solve it with normal CFT methods. Again, you see, great agreement. 3D ON model at large n. Again, where we had the exact solution, you see all the points are super nice. And now we start getting to more and more unknown territory. So still, for the Ising model in 3D, we have something to compare. And this is, first of all, the Monte Carlo simulation, and then the paper by Luca and Eric, and I think these are the only people that are here. So, and again, you see that there is very, very, very good agreement. So this method looks good. And because it's easy and basically sort of universal as a method, it is very easy to just continue and predict what happens for the O2 model, what happens for the O3 model. Not really a problem. And here maybe a cute plot. So here we have plotted epsilon is the 4 minus d. So here we have the 4D free theory. Here we have the critical 3D theory. And here we use the conformal dimensions in the epsilon expansion. And you see, even if it should have not really been so good, magically, the stars are the, when you do the calculation on 3D with the bootstrap answer for 3D, the results are very, very good, very, very close. Here is another very important thing, again, plotting the two-point function. And when you look from far away, they look on the top of each other, you think it's perfect. When you zoom in, there is a little bit of a difference. This is the failure or the error that we make to satisfy the KMS. But you see, the work that we did was nothing. We didn't even try hard to make accuracy. We basically, all of these plots that I showed you, they can be made in a couple of minutes in a normal laptop. And we didn't even try very hard. We said, oh, let's put 3 light operators and see what happens. And we didn't even keep many derivatives. So with basically almost 0 effort, you can get this very beautiful accuracy here. Okay, a little bit about temporal line defects, because there also you can play the bootstrap game. So, okay, I don't need to say anything in this audience about Polyakov loops. They are introduced as a criterion of confinement, and of course, if I am turning on the temperature, I need to ask, can I compute them? So let's try to see what we can do. So the normal 0 temperature bootstrap, there was a whole subfield of research within it that studied defect CFTs. And what you do, for example, when you have a line defect, you have a 1D defect CFT that gives you the answers. So what we do now is, first of all, we need to use our 0 temperature bootstrap data. And in this case, we take a bulk operator, and we OPE it on the line. And these are the OPE numbers that we need to get from the 0 temperature bootstrap friends. And then what we do, this is just an example, but this is a 1-point function of a bulk operator in the presence of the Polyakov loop. You can rewrite in this form, so everything is 0 temperature bootstrap. And there is, again, like before, a linear dependence on the new things that we need to calculate, which are vevs due to finite temperature in this 1D defect CFT. What do we do? Again, we do the same. We know KMS, and we go with it. So here is the KMS condition in the presence of a Polyakov loop. And we just do the same manipulation identically as before. And these are now the new sum rules in the presence of a Polyakov loop. And these are, again, as before, an infinite number of linear equations for this new data that we need to solve. And what is very important is that basically the form of this equation is the same as the equation for which we developed the numerical method. We haven't done yet that, we haven't solved it numerically yet, but I cannot see how we will not be able to do this. Let me start concluding. So what have we done? So first of all, we have derived and tested thermal sum rules, maybe with special emphasis on this R equal to 0 case, where things become very beautiful and easy, and you can solve very nicely. Then, turning to heavy operators, this was a very important lesson. We were able, using Tauberian theory, to compute the asymptotic thermal OPE density. And also, we made all of these plots, and we saw that, oh, this Tauberian approximation is very good. And then, inspired by that, we proposed this very efficient method to do numerical bootstrap. I want to stress, this is a couple of minutes in your laptop. This is, like, I never wanted to have to do harder computations than that, yeah? And maybe what I should also stress is that all of this Tauberian thing, it looks so powerful that maybe people should really look in other little corners of the bootstrap, maybe even of the S matrix bootstrap. Maybe there, this should really be used, and it will make things much easier. Yeah, so we have our technique, And then I said a few words about Polyakov loops. There is much more to be done there. And now a little bit about the future. So this is not even a future in some sense, this is now. While I was having a Christmas vacation, my amazing thermal heroes were calculating like crazy. And we basically have it. I was just not able to digest it before coming here and to present it. We have a nice analytic approach, which is based on something like what Sasa presented a couple of days ago, a thermal version of the dispersion relation tricks, which is very, very, very beautiful, and also for me is very important because it's very complementary with the numerical. So I think these two things going hand in hand, they will really allow progress. The other thing is more theories. So we stayed for simplicity in 3D and we did all these ON theories, which are great. But I don't know, especially where I come from, I want to do the CFT, I want to do n equal to 4, I want to do ABJM. And by the way, for this theory, we already have results for n equal to 4. So it's really like it's not a far future dream. And the numerical method is really made to do this. No problem. Yeah, then I already said that the numerical approach for the Polyakov loops is one of the most important next steps. Then here, this is very important for physics. So up to now, everything that I showed was S1 times flat. But this is what we really want, because we want both. Because, for example, in large N, Witten told us that we have this phase transition, confinement, deconfinement. So if you ever want to be able to see this doing bootstrap, you have to have also this, and then you have to compare. You have to make a plot, and yes, see the phase transition. And then, okay, moving more into the future, but actually I really don't think that this is our future. We already have a tiny little bit that we have started playing with. Really start learning lessons about the black holes. Julio's talk was very inspiring because I was also thinking, oh, quasi-normal modes, love numbers. So I think this can be calculated, no problem. And another thing that I think can be done very nicely is the hydro stuff that was very fancy in the early days of EDCFT. Can we calculate that as a function now of the thermal data? Yeah, and with that, I just thank you.
Thank you very much. We have time, so Juan.
Yeah, so if you start with a field theory that has, let's say, a gravity dual, so then the low line operators are all known.
Yes.
Can you do this program and
Yes.
find?
Yes.
So can you find the actual value of the free energy?
Yes.
So without solving the gravity solution, but just directly.
I just didn't want to show in this talk anything that is not published, but we can already do some of these things, and some of these things will come out. Yes, soon.
Okay, Kamran.
Very nice talk. Probably my question is trivial because I must have missed something. Why don't you just use brute force by method of images?
No, I didn't use brute force.
I'm just saying, why don't you use brute force?
For interacting theories, it's
no,
not
I mean,
that.
if you have OPEs, if you have a one-point function on a circle, you just put images of all of them, and if you have all
For the one-point function, it might work, but in general, I always wanted to
But I thought
do
you got from one point, you got the whole data. Am I misunderstanding?
From where? So for the Tauberian approximation, maybe.
No approximation. If you want to compute the one-point function of your operators.
Yeah, I don't think you can always just do that.
Why not?
So what I always wanted to do is that I wanted to use this formula, basically.
No, I mean, what is periodic thing other than putting images? What's the difference?
I mean, I understand, but I don't think it's that simple.
Why not?
I think I have tried, and I don't think it always works. And maybe I can say it in different ways. This would be one example that satisfies the KMS condition, but there are also other functions that satisfy the KMS condition. And it can be a linear combination of all of these examples that satisfy the KMS. And you have to find the one that corresponds to your own theory.
No, but KMS is not the only thing. The definition is periodicity. The definition is putting the images. Circle is periodic.
Okay,
So
maybe
putting
we
this
can
emission
talk
is
more
different.
because maybe I'm missing something, but I don't think it's that simple. If it was that simple, I think it would have been solved by now.
Okay, Eric?
Just going back to the first question.
Yes.
Are you saying that with these methods you think you could access this famous 3/4 factor in planar n
Yes.
equals 4 at strong coupling?
This was a private discussion, but yes.
You think the answer is yes?
No,
you can
we
get
have
that?
the three, yeah,
You have
three-quarter,
the-
we have it.
Do you have a function of the
But
thermal free energy
this is
as a
going to
function of
come. Give me a
lambda?
month and you will have a paper with 3/4.
Okay.
So this was an announcement. So any other question?
Yes.
Okay. Oh, okay. Right there, Sasha. Yes.
I wanted to ask your numerical algorithm prediction. Can you put an error bar?
Yes.
Or estimate error?
So I have to say, I am absolutely not happy with the way we estimate the errors. I can explain what we do, but I think, and this is also now why the analytic approach is very important, this will really nail the way we estimate the errors. So the way we did it here is that we were always comparing, so there is a statistical error which you can make very small, is not a problem, and then there is a systematic error, which actually you can already see here, everything goes a little bit up. And the systematic error, I can explain it very easily, and you can see it here. It's basically in these dots. If you could, the more corrections you add there, the more your system, we have in the paper plots where we demonstrate this, the systematic error goes down, yeah? Yeah, so it's just that at some point you stop and you accept a systematic error. Is this a good enough answer?
I guess I would like to see a rigorous error bar, right? So
Yes,
this
so
prediction with a rigorous error bar.
the
My
honest
impression
thing
is
right now is
yeah.
that the error bar that we have, the systematic part of the error bar is by always comparing with a free theory. But now that we are doing this analytic method, we will be able to give you a more rigorous. And we will also be able to add these dots and really nail it.
Okay. No other questions? Going once? Okay. If not, let's thank all the speakers in this.
We reconvene at 2:30.